Hello class, today we're going to go over three-phase circuit calculation. First, we are going to have a three single-phase transformer. Let's say one, and this is one single-phase transformer. And then this transformer has a rated capacity of 10 kVA. And then is ground voltage, line to ground voltage from here. This is to the ground. That would be from here. This is the neutral. So this is phase A. Then this voltage is 700 volt. Okay. And then on this side, it would be 120. Okay. So the reason that on this side it has a 2 voltage is because usually in the distribution circuit, you get this connected to the ground. Okay. Then this voltage is 120. Okay. And then the voltage across these two legs are 240. Okay. So today we're going to only study the high voltage side. So we have 3 of them. We form a three-phase transformer. So there's another one. And then this is connected here. And there's another one. So you can see that on the high voltage side, this is connected with the Y connection. Okay. So if that's the case, then this is our B winding, this is our C winding, and then this is our neutral. Okay. So in this case, we're going to see that for this new three-phase transformer, what is the rated capacity, the rated voltage, and the rated current. First, for this single transformer, the capacity is 10 kVA, so it's 10 kVA, and then the rated voltage is 7,200. So in the first case, we're going to use this 3 single-phase transformer to form a Y-Y connected. So the secondary side is also connected to Y. But we're going to study only the high voltage side, or only look at this side, okay? Then we want to see what's the new, for this new transformer here. So this is our new transformer. What is the rated capacity? So for each winding, it is rated as 10 kVA. So for 3 of them, we can say that it's 3 times this winding because it is sustained current and voltage. Each can carry 10 kVA. So for 3 of them, it can carry 3 times the single transformer's capacity. Okay, so that's 3 times that. So next, we're going to compute for the line to neutral voltage. So for Y connected transformer, you have this directly connected this phase from a line to neutral, A to N. So this line to neutral winding rated voltage would simply be this rated capacity, okay, just like that. So that would be VHLN line to neutral, okay. So that voltage is simply equals to this rated voltage, okay. For the line to line, because we have this, we're going to learn that from the course that we have this is our line to neutral. This is our VA, and then this is our VB, and this is our VC. So our line to neutral voltage is this, and then line to them voltage actually is here. It's VAN minus BN, okay? So if VN minus VBN equals to VAN plus VNB. Okay, so that's why this is like that. So this is our VAB. So the magnitude of VAB obviously is longer than that because this is a 30-degree angle. And then you can see that this part is 2 over square root of 3 and times 2, because this part is like that, right? You use this times this cosine 30, and then you have to times 2 because that is 2 parts. So you times 2, then you can get that VAB equals 2 square root of 3 times VAN. And then the angle here is 30 degree, right? So it's leading 30 degree. But here we're only calculating the magnitude. So what we have is simply use the square root of 3 times BLN, which is this line to neutral voltage. So this is how we calculate the line to line voltage. And then next we're going to compute for the current. So one way to compute this current flowing through here is simply using the phase voltage, line to neutral voltage, and then the capacity of this single phase, right? So we have the power, the rated power for the single phase winding at 10,000, and you can simply use that to divide this. Right now, we don't consider the power factor. We are assuming that this is power factor is 1.0. Then we can just compute for the magnitude using the S divided by N. That's one way to compute this phase current, right? Because you have a capacity, the winding capacity stat, and you have a winding voltage. And the other way to compute for the line current in the textbook, you can see that it equals to, this is your 3-phase rated power, and then divided by 3 times V line to line. So that's another way to compute the current, the line current. But in here, if it's connected in by, the line current will equal to the phase current because it directly flow into the phase. So this is another way to compute that. You use a 3-phase capacity, which is simply 3 times this, okay? And then divided by square root of 3, and then divided by the BLL. So you can see that this actually equals to BLL simply is square root of 3 times VLN, right? And then this is S3, yeah. And then this is simply equals to 3. So 3-phase divided that, so that's simply equals to S1 phase, and then divided by BLN. So you can see that these two are actually equivalent to each other. So if you run this code, you will find both will give you the same value. So you can use either way to do that. But you need to be aware of that this particular formula is used to compute for the line current here, okay? So next, we can say that for this Y-connected transformer, the line current equals to the phase current. So line equals to the phase. So you can just do that. Okay. Let me just move this a little bit down. So next, we're going to compute for the loss quantity, which is the impedance here. Okay. So the impedance, there are also 2 ways to compute for that. Let me see if we can clean this up a little bit. This up. Okay. Now, we would see that there are also 2 ways to compute for the impedance here. So this is the Y-connected equivalent load impedance here, meaning this is my voltage. What would be the equivalent impedance connected here? Because it's Y-connected, so this is A, this is N. So if we compute this equivalent impedance, we can use the VLL divided by the three-phase, like this is a VLL, the square, and divided by the three-phase power. This is one way of compute for the equivalent impedance for a Y-connected load, right? And then the other way is directly use the voltage, line to neutral voltage, and then divided by the current, the phase current, the I phase, right? So you can see that if we do this calculation, both will work. They give you the same value. Okay, so you can see that I can either use Z equals to V line to line, the square of it divided by the three-phase capacity, or I can simply use the phase voltage, which is line to neutral for a Y-connected load, and divided by the I, the phase current here, right? So the voltage divided by current equals to Z, right? So here we're computing purely the magnitude of it, okay? So that's why we don't have to consider a power factor. So in this case, both give you the same value. If you run that, you can see that this gave you the same value, okay? So this is basically, you need to go over this in detail. So that tells you if you have a three-phase capacity or single phase capacity, how you compute it for the voltage and the current. And then you can see that for three-phase circuit, different from the single phase circuit, single phase circuit, you only have this one voltage you need to be aware of and taking care of. And then that's the voltage across this winding. But for a three-phase circuit, because there's a transformer, and then depending on the transformer connection, you can see that if this is a Y-connected transformer, then there are two voltages of concern. One is a line to neutral, which is here, and then the other is a line to line, okay? So the line to line voltage here is actually have a magnitude of square root of 3 times higher than the line to neutral voltage. So this is AN, which is line to neutral, okay? So there are two voltages. But the current, the line current here, because the current directly flow into the phase. So in a Y-connected transformer, the line current equals to the phase current, okay? So next, we're going to just go over this real quick. What if this is a delta connected case? So for delta connected case, what we have is we have, this is our first transformer. Now I only draw the high side just to simplify that. And this is a second transformer. So we connected the head with tail, right? So this is A, and then this is the end of it. And then I connect that directly with B, the head of B. And then the end of B will be directly connected to the head of C, okay? And then after that, we connect the head of A with the tail of C, okay? So eventually what we have is that we have, this is incoming, incoming, and incoming, okay? So this would be a delta connection, right? So if you think of that, it would be something like this is A, B, and C. So you're connecting them head. This is A, the tail with a B. So if you have a polarity, so this is a polarity. So with the polarity, this is the head, right? So this is A and B and C. So head to tail, and then head to tail, okay? So that's how you connected a delta. And then this would be that. This will be A and B and C, okay? So this is similar to this connection. So when you do that, now what it's changed. So here your winding, this is your winding voltage here. This is winding voltage. So the winding voltage is no longer the A to neutral, because here the neutral is not inside here. So this voltage simply equals to VAB. So now your winding rated voltage is actually the line to line voltage, right? So this line to line. So if you want to compute for the line to neutral voltage, you will need to divide by square root of 3 here. So you can see that you need to take this voltage and then divide it by square root of 3. This is because right now your connection is like this is your VAB. And then your EC and VC. Okay. So your if you want to compute for the VAN, is something like this. Okay. So you need to divide by square root of 3. So this is here times the square root of 3. But if you use this to compute VAN, you divide it by square root of 3. Okay, so this is how you do that. So now the current is also different. So this is a current N, right? And then you can see that now the current here, it is no longer equals to the line current. Instead, the phase current and the line current actually has a square root of 3 relationship. So now your phase voltage, on the other hand, VAB, this is a phase voltage, and then it equals to the line voltage. So VAB equals to this phase voltage now. Okay, you can see that. So for the calculate the phase current, how would we do that? Again, we can use the capacity divided by the phase voltage. So now the phase voltage is simply VAB. So you can just say, well, we use this, this is our 10,000. Okay, and then divided by this, okay? Because this winding voltage would be the line-to-line voltage now. And then the other thing we can do is to use the line voltage. So line current. So line current would equals to, remember, it's a S3 phase, and then divided by square root of 3 times VLL. However, this will calculate this current. But if we want to compute for the phase current, we need to divide it by another 3 here. So that's how this square root of 3 comes in. Okay. So this gives us the line current here. Okay, this is IA. However, this phase current is IAB. Okay, and then this IAB actually has a square root of 3 difference. Okay, so in class we talked about that. So if you want to compute for the line current, which using this equation, the 3-phase capacity divided by square root of 3 and divided by line-to-line voltage, you need to divide it by another square root of 3. Or you can simply just say, hey, the line voltage equals to I phase times the square root of 3. So once you calculate the phase current by using the single phase power divided by the phase voltage, you can use that times square root of 3. So either way, you can use that to compute for the line current. So again, when we compute for the impedance, we can use this Z Y equals to VLL square divided by S 3-phase. But this Y connected load, and then when you're connecting this as a delta, if you want to know the delta equivalent impedance, what you have to do is you actually have to times a factor of 3, because like this is a Y-connected impedance. So if you change them to delta, you times 3, right? So that's why you can use this formula to compute for the Y-connected load. But if you want to compute for delta-connected impedance, you need to times this particular value by 3. So this is the same and times that by 3. Okay. So the other way of doing that is because you can also just directly use this voltage here, the voltage across the winding, which is VLL, VAB here, and then divided by the phase current. Okay, so this is the phase current we compute. So that is another way of doing it. So if you can see that both will give you the correct impedance. So this is the Y-connected one. You can see that there's a factor of 3 here difference. Okay, so this is how you are going to compute for the line-to-line voltage, line-to-neutral. I think this is the biggest confusion usually student would have. So for Y-connected or delta-connected circuit, you can see that for Y-connected one, you have this line-to-neutral voltage. And then you also have this line-to-line voltage, right? And then in this case, the current, the line current equals to the phase current, okay? But for delta-connected circuit, you have this line-to-line voltage. It equals to the phase voltage because this is across this phase. So the VAB equals to this phase voltage. However, the current is different in this case. This is your line current. It flew into it, and then it flew 2 directions. So this is IAB, and this is IAC, right? So in this case, your IA actually equals to square root of 3 times IAB. So this is the magnitude. There's also an angle which is lagging this, and then we can talk about that in class. But you can see that in this case, for delta-connected load, the current of the line current is not equal to the phase current. And then for Y-connected load, the line-to-line voltage is not equal to the phase voltage. Okay, so they all have a square root of 3 relationships. So you can play with this code. I'm going to post that on the GitHub. Thanks.